Right, so today we're going to, before lunch, we're going to hopefully talk a little bit about quite a new concept that perhaps most of you haven't considered, actually combining the ideas of allocating memory in software with transactional databases, so combining these features almost into one tool, making it more accessible for programmers. Next slide. So, I don't know. So just a quick overview. We're going to, first of all, we're going to kind of paint the problem as what are some of the current existing problems with databases, and particularly in relation to applications such as size with Internet of Things and machine learning. We're going to rethink the problem in a basic concept. Discuss some of the technical issues with Rockall-DB, go through some examples and hopefully a demonstration, and we'll conclude. Next slide. Just a little bit about us before we kick off. As you can see, we're sort of from different backgrounds. Michael has done some work on compiler internals and databases, particularly with Microsoft. And operating system internals as well. Myself, working at doing research at Southampton, mainly in biological modelling using machine learning to predict protein concentration.
You want me to take? Okay, so I'll kick off on the next bit. We all love transactional databases, or maybe we do or maybe we don't. I would argue that a lot of transactional databases today are relatively complex. You know, it's not something that you wake up at 9 o'clock and you can use them by midday. Inflexibility. This is just some of the database types that there are out there. I would argue that I'd like a general purpose database. I really don't want to pick any of them. I want something that works all the time. Performance. I saw this thing on Google the other day, I believe it was, and they said that on their database could respond in milliseconds. I like microseconds. That sounds good. Picoseconds is better, but microseconds is what I'm hoping for. And bloat, particularly with commercial products, like Oracle or SQL Server or something like that. You know, it's measured in gigabytes. Clearly that doesn't work in IoT. There's a whole range of areas where that doesn't work. So my personal prejudice, I've worked on database internals, but I hate databases. I'd like to do something different. So that's where we're starting. Okay, so I don't know whether there's people who are familiar with databases in the room. You may have background and experience, but with a wry smile, that's not going to help you in this presentation. Because if I may, I'm going to start from a clean sheet of paper. And I'm going to say memory allocators, malloc, realloc, free, new, delete, allocate memory really well. They're really good tools. So how about using these to do a fully ASCII-compliant transactional database? What would it take? Can we really get a database with simple APIs like that? So let's have a go. Let's see whether I can talk you through it. All we're going to start off with is we have our favourite APIs. Let's say malloc for the sake of argument. So all we're going to do is we're going to add one new parameter. File address. So with malloc, you know you get a memory address out in the end. You have to supply a size. We're just going to add this one new parameter, file address. And what we're going to say is that when we call the memory allocator, it will at the same time allocate file space. Now, what do I mean by file address? Hopefully it's obvious. I really mean that if you go and look in the file and that file address says 123 as the address, if you go and look at byte 123 in the file, that's where your data is. So what you see is what you get. And we can do the same for realloc, which in this case we're going to call resize. Delete. Now here that you'd normally give a file address, but you could give the memory address if you wanted to, it's still deleted. So that's what we're going to try to do. That's going to be our basic change. We're going to add one parameter. Now, if we're going to do a transactional database, guess we're going to need to create some files, open files, close files. So obviously you're going to need those APIs. Pretty difficult to do transactions without begin transaction and end transaction. And one thing you'll see later is you're going to open one of these files. There's going to be stuff in there, and you'll want to fetch it back. And you'll either want to update it, or you'll want to view the data that's there. So our proposal is, with 10 APIs, you can have a transactional database. Right, that's what we're going to try to demonstrate. Okay, is that any questions on that? Because this is pretty key. Right, on to the next. So I've long believed an example is worth 1,000 words. So this is very, very simple, but it's just our first little example to try to help you understand what this might look like. So we're using C++, so hopefully that's okay. Got a couple of includes. Hopefully they're, no big deal. There you go. There is your transactional database. That definition. You can have as many as you want. You can even have an array of them if you want to. If we go further in later, you'll discover that you don't have to have a transactional database. You could just have a good old-fashioned heap. It supports various things. In this case, it's a transactional database. Now, that's not a lot of use until you link it with a file. In this case, we're creating a brand new database. And there you go, there's the call. We could open it, but in this case, we're creating. You have to begin a transaction, obviously, transactional database. And in this case, we're only doing one call. We could allocate space, we could delete space, we could resize it, we could do updates. So you could do hundreds of calls in there. We're just doing one in this case, which is saying, please give me a space for a char14 array. There's the heap. There's our file address. There's the memory pointer. So we struck copy in. Hello world. Right? And here's the key call there. End transaction. Whatever you do between begin transaction and end transaction, whatever you allocate, whatever you delete, whatever you resize, whatever contents you stick in memory locations, end transaction will say you get them all or none. Okay? Now obviously it's just a single allocation here. It's a pretty simple example. But hopefully this is giving you the idea of what it might feel like. And in this case, I'm finished now with my database, so I'll close it and I'm out of here, I'm gone. So is that all fairly clear? Okay, next. So, let's try to preempt a few questions. The first question is in normal databases, you have a row limit. 8K, 16K, whatever. This has no row limit. So if you have got a lot more money than I have, and you can afford a couple of terabytes of DRAM, you can have multi-terabyte allocations. So, if you've got a vector or a 2D array or 3D array or whatever, you can allocate as much as you want to, and it will all be done atomically. Right? You get all or nothing. Whatever. If you think about it, this can sometimes really simplify applications. For instance, I wouldn't want to have a 1 gigabyte array and try and put it in a JSON document and store it in Mongo, for instance. I don't think that would work well. Certainly wouldn't work in SQL Server. Full ASCII compliance. That end transaction means what it says. You get all or nothing. Multi-threading. Now, one thing I didn't talk about initially is the whole question of locking, which goes on quietly in the background. Because when you say, I want to allocate some space, actually an appropriate lock is taken. When you want to realloc or resize something, suitable locks are taken. If you update something, or two people try to update the same areas of memory, proper database locking occurs. You don't have to ask for it, it just happens. Automatic deadlock detection. Say thread A tries to update this allocation and thread B tries to update this allocation, and then they try to update each other's allocation. It will detect that. And it will say, no thanks. And one of the updates will come back and it will say, you've had a deadlock. And it's interesting here because it doesn't blow you away immediately. You can choose to commit at that point if you wish. Or you can just abort the transaction, which is what you'd normally do. You have a choice. Parallel transactions. You can have multiple threads operating in a single transaction in parallel. It's perfectly fine. Right, so, you know, if you've got a couple of hundred threads and you want them in some transaction for some reason, that works. Replication. I said that we were going to open a file. It turns out you can have multiple copies of that file, possibly separated in different places around the world, and they are in perfect synchronization to the millisecond. Because what happens is the write to the database goes to all copies of the database. You can currently have 4. There's no reason why it can't be higher. That's just generally enough for most people. And obviously a synchronous read ahead. You can get the I/O system going ahead as far as you want to. There's a whole discussion to be had there. So what we're trying to do here is to do something a little different. Normally, you'd have a database which would be this big honking exe, and in there you'd have indexes and all kinds of stuff. Here, it works the other way around. You have a very small core, which you'll see, which is under 1 megabyte. And because the core has the right APIs, indexes are actually external. And interestingly, in source code form if you want them, and they're templated. So if you want a custom index for some funky key value, returning some funky data value, any types of your choice you can use. And you can even reshape an index. So say you've got a tree, you can decide whether you want a broad flat tree or a narrow tall tree. So your index branching factor can go from anything from 8 to 32,000. So that's a heck of a range. And different applications want different things, depending on whether you're inserting and deleting quickly or whether it's mainly read. Because there's a core, and because it's so simple, the functionality for relational databases is in there. All the set operations you need, row sets and so on. And you can put that in and use it on the core. If you want an object-oriented database, hopefully you can see that's pretty obvious, because when you do that new, you can actually execute constructors and destructors at the same time. I mean, it's so object-oriented, it's, you know, you don't even notice the difference between that and main memory. And really where we're heading here is, if you really think of what we're doing, the transactional database here can do anything that a normal main memory allocator can do. The only difference is this file address. So anything you can build in main memory, anything you can dream of, if you can build an XML document in main memory, if you can build a JSON document, whatever you want, you can have. If you can store it in main memory, you can build it with this database. Come on, I was really expecting some pushback there. Okay, let's go. So, couple of points. there's a boatload of caches in there that I haven't really talked about. So obviously, if you go and bring in a piece of data to look at, there's a buffer cache in there as there would be in Oracle or SQL or whatever. You can control that in any way you wish. The default is 10 minutes retention, but you can pick any number you want. Obviously, if you start to run short of memory, it does LRU like you'd hope for. There's also caches in the way it does allocation. So you don't go to disk when you want to allocate memory. I mean, it runs at about the cost of an operating system call. So that's not cheap, but you know, a microsecond or something of that nature is what you'd sort of pay. Just want to get rid of a couple of misconceptions. This may look like a memory allocator. This may smell like a memory allocator, but this is not a memory allocator, and you are not limited by DRAM size. You can have multi-terabyte files with just a few gigabytes of DRAM. Now, obviously, you can't make an allocation bigger than DRAM, because obviously the operating system will freak out underneath you and go, "You're killing me, there's not enough space." But the database size is not limited in that way. We do not use memory map files. Now, I'm only mentioning this in case there's people who are familiar with databases in the room. You cannot get a proper ACID transactional database with memory map files. Things like torn writes just blow your brains out. So that often comes up, people think this is memory map files. It isn't. Right, okay, so I'm just about to do a demo, just because I believe seeing is believing. Any questions up to this point? Okay, so what are we going to do with this demo? We're going to take a book. We're going to build a reverse index. Hopefully people know what reverse indexes are. If not, think of Google. So we're going to build a reverse index, and then we're going to search for this book to find certain keywords. So sort of Googlish. So the book. So it's a bit tricky to come up with a book, because I need a book that you've all heard of and that you all know of. And of course this is research, so it has to be free as well. So I'm sorry about this, I hope no one minds, but the obvious choice seemed to be the 1611 or whatever it is, King James Version of the Bible. You know, something people will have heard of. They can feel what the book's like. So that's what we're doing. So let's look at what we've got here. We've got our program, book.exe. You'll see a bit more about that later. We've got our book. There it is, 4 megabytes. Dump.exe, that's something you can see later, where you can see the binary image of the database. And Rockall-DB, there you go, that's the full transactional database. The whole enchilada. Okay, so let's try our first step. So what we're doing now is we're building our reverse index. And what we discover is there's evidently 791,000 words. I didn't know that. 12,000 unique. There's 580,000 paragraphs. And there's our database there. Book.db. And we built that live. Right? So let's go on to the next bit. So just in case you ever wanted to know what words were in there, here you go. So I did that by walking the index. As we said, there's 12,000 words. I've never heard of half of them, but gives you an idea of what's there. Okay, and you're welcome to look through those, or you want to copy this after, you're welcome. Next. Okay, so this is our first little demo. And all I've done is I said, let's go and look in there. And we're looking for 2 words, crow and twice. Any 2 words. If you want to do this live and you want to do different words, feel free. And in this case, bang, that's what it comes up with. Now, this is really the silly example. Let's now get on to a more serious one. Why don't we do the query from hell? So why don't we do is, of, the, every word with a huge count on, and see what we can come up with. Right, so hopefully you saw that. It's basically like that. And the words we were looking at are there at the top. By, for, his, I, in, is, my, not, of, the, to, will. Just run that one again. So just watch carefully. Now, just to be clear, this is from a standing start. When he clicked that, the database wasn't up. Nothing was in main memory. Nothing was pre-prepared. That was from stand up, open the database, search through that lot, print it out, close it down, go away. So I'm now just going to spend a couple of minutes, I'm sorry I'm a little short on time, a couple of minutes just taking you through what a still small example, but what that looks like. So we're going to start off here. A couple of includes, who cares? So go on, stop there. There is the definition for my index. It's configurable. I'm saying I don't want any locking in. I could have locking if I wanted to. I'm saying that the key's a string, and I'm saying that in the end I produce a file address. String could be anything. It could be an int, a float, it could be a struct, a union, whatever you want. And the same for the file address. You can have anything you wish there. I'm just picking something simple. I won't bother talking about strings. It's not worth it. Stop there. That'll be good. Here, those are all the data definitions for the entire application. That one there is the root one. That's at the base of my database. That one there that stores the entire booking. And that one there is a pointer to every paragraph I come to. Okay, carry on. It's going to be quite a bit. Stop. So now let's go and look a bit more and look at a bit of the code. So yeah, a bit more if you can. Stop. That'll do. So hopefully you're going to recognise half this stuff. There you go. I'm creating a database. There we go. I'm bidding in a transaction. Up for this. Now this is the meat and fish of most of the tool. The first line creates the root of the database. The second line creates space for the entire book. In fact, I'm going to read the whole book into a single row in the database. Is that a good idea? I don't know. I'm doing it because I can. So this text file read there, that just does an F-read. It just opens the book, swallows it in one go. I'm not going to cover that today. That's just a basic piece of housekeeping. So a bit more. Stop. That's the end of my transaction. Talked about that before. That's closing the database. We're done. There's only two other pieces of coding in there. One dealing with a paragraph and one dealing with a new word. I'm just going to deal with the new word. Go on. Stop. I'm going to be around here somewhere. Let me do this because I'll get it wrong. That's a bit further. Here we go. So this is the last bit of this. So quickly run through what you do. You can see that the first we turn it to lowercase. Here, this is just a simple tree lookup. It comes out one or two ways. You put your word in, and either A, I've seen this word before, and in which case I find the row set and I add it in. I add the reference in. Or B, it's not in there, in which case a bit higher. In which case I'm not in there, in which case I create a new row set, I put this reference in, and I put it in the index. Done. So hopefully you'd see that's not overly complicated. And that's all the database code there is.
Right, just quickly, last minute, I know you guys want to eat lunch. Obviously, there are many applications to this, tons of talks here on the Internet of Things. One of the great things with Rockall is the small size means it goes well with storage of a lot of the devices that we're planning to port onto, and also the full transactionality means that devices where you have issues of power, you're not going to lose that data. It's actually going to be fully ASIC compliant. Yeah, and those are our details. I don't know if we have time for questions.